on intermolecular forces of attraction today and just focusing on initially identifying them and understanding what they are and their relative strength to each other. So first off, one thing to distinguish is between intramolecular force and intermolecular force. So an intramolecular force is going to occur within a compound, such as an actual ionic bond or an actual covalent bond. And when this is broken, we can potentially have a chemical change, depending on what material you're dealing with. When you talk about intermolecular forces, think of like an interpersonal relationship or an interstate. It's going to be between two things. So an intermolecular force is going to be between two molecules, and these are attractions that usually deal with like partial charges or become between ions and molecules. IMFs are relatively weak compared to the primary intramolecular bonding forces. Usually when we deal with intermolecular forces being broken, we're dealing with physical changes. All right, so comparing intramolecular forces to intermolecular forces, one thing is when measuring the distance between atoms bonded in the same molecule, the intramolecular force, and the distance between adjacent non-bonded atoms, we're going to find that that intramolecular distance is much smaller than the intermolecular distance. So in this case, let me just change this so you can see it. We're dealing with, here's the bond. Okay, in this case, covalent bond. This distance would be much shorter than the attraction between them, or this intermolecular force of attraction. And again, it has to do with the fact that this is an actual bond where those orbitals are, in this case, overlapping compared to just an attraction between. So the energy involved, you'll see a big difference here when you look at these two values. You can see that the amount of energy to overcome the intramolecular force is 930 kilojoules to break all, say, the OH bonds in a mole of water versus 41 kilojoules just to vaporize. And we talked a little about vaporizing before. So let me see if I can get this to work. So it takes much less energy to overcome, which I usually like to say overcome an IMF, not actually break an IMF, but to overcome an IMF than to break a chemical bond. So we'll be keeping that in mind as we go forward. So in terms of our intermolecular forces being much weaker than the primary bonding forces, they influence physical properties such as melting points, boiling points, vapor pressures, and so on. So let me just take this off so you can write this down. The stronger the IMF is, the more energy it's going to take to overcome that attraction or overcome the IMF. So the higher the melting point and melting point, boiling point, the lower the vapor pressure. We'll talk about vapor pressure in a future unit. We're going to mostly focus on this lesson and the next lesson on melting points and boiling points. Okay, so the stronger that attraction, the more energy. So what creates stronger attractions or weaker attractions in terms of intermolecular forces? So our first IMF that we're going to deal with are our London dispersion forces. These attractive forces are present in all atoms and molecules, whether they're nonpolar or polar. However, this is the primary IMF between nonpolar molecules. So you're usually going to relate London dispersion forces, which you will see from time to time as LDF. Okay, it's just a short abbreviation for it. Let me just erase this here. All right, so LDF is present between polar molecules, but it's not the primary IMF. So just keep that in mind. We're always going to be identifying LDF or London dispersion forces with like our polar molecules, but we're going to focus in usually on the dipole-dipole, which you'll find out about shortly. All right, so what is these London dispersion forces between, especially we're going to focus in on nonpolar molecules. So London dispersion forces are a temporary instantaneous dipole thing can be created that's caused from a temporary uneven distribution of electrons around a nucleus. So for example, if we have an atom of neon, okay, that's going to be nonpolar, at any moment in time, its electrons may get distributed unevenly around the nucleus. You can see in my depiction, they're kind of clustered over to the right-hand side versus the left-hand side. So when that happens and it becomes uneven and it's temporary, we get slightly partial negatives and partial positives, very tiny, that form. Okay, and then those small partial changes interact with each other. So interact with another atom of neon. Okay, so again, it's a temporary instantaneous dipole. And dipole, remember, would be these little partial positives and negatives that then will interact with another atom and create an attraction between it. Okay, because this is temporary partial positives and negatives, it creates a relatively weaker attractive force than some of the other ones we're going to talk about. Sometimes it can actually be stronger, which we'll deal with. So the tendency, or how easy it is for an electron cloud to distort, is called polarizability. Okay, I would highlight this. This is incredibly important. You're going to hear me talk about polarizability a lot the next couple lessons. So what influences polarizability? So one big thing is that polarizability is going to increase with the number of electrons in an atom or molecule. It's going to increase or be influenced by the size of the electron clouds, and it's also enhanced by pi bonding. So let's take that first one, number of electrons. The more electrons, the more the electrons can become distorted. So the greater that temporary partial positive, partial negative will be, which means that you're going to create a greater or stronger attraction. So the more electrons, the greater the polarizability, because the electrons can be distorted more, which is going to create a stronger attraction. The size of the electron clouds, which really, if you have more electrons, you're usually dealing with the size of the electron clouds. The larger the electron cloud, so let's say we have an atom that has the 4th energy level versus another atom which is only going out to the 2nd energy level. The ones that are in the 4th energy level, we know from Coulombic attraction that they're farther away. They're not attracted as strongly. So that means that those electrons are going to be more easily distorted. So larger electron clouds have a greater polarizability, which is going to create a greater distortion, which will actually cause a greater attraction. And finally, pi bonding isn't as common, but it's important because it will come up in some questions as being the only really way to distinguish it. So a sigma bond is directly between the carbon atoms. But say these carbons have a double bond. The pi bonding forms above and below that sigma bond. So what we find with pi bondings, which is again are in double and triple bonds, is that because they're formed from the side-to-side overlap, they can be more easily distorted. And again, when you have electrons that can be more easily distorted, it has a greater polarizability, which means it's going to end up having a greater attraction. So if we look over on the right-hand side here, you'll see the halogens and the noble gases, and you'll see their relative melting points and boiling points. I think in this case, they're looking at boiling points. So as you go down, you'll see it increases. So why does the halogens boiling points increase as you go down? Why does the noble gases boiling points increase as you go down? And it has to do with polarizability. So the more electrons and the larger the electrons clouds get, the greater the polarizability, okay, which means a stronger attraction, a stronger London dispersion force, which is going to result in a higher boiling point. Okay, so this is going to be huge in terms of talking about and being able to understand and discuss polarizability. The strength of that London dispersion force also increases if you have a greater contact area between molecules. So whether they're able to have more contact, say if they're parallel with each other rather than next to each other. And just keep in mind, we just talked about increasing polarizability. So the greater the polarizability increases, the strength of the LDF increases. So it takes more energy to overcome it, which is going to result in a higher melting point and boiling point. So London dispersion forces and polarizability, I would almost pause this and kind of read back through it for yourself because it's going to be a big part of our discussions over this unit. All right, another type of intermolecular force of attraction is dipole-dipole forces. So in addition to London dispersion forces, polar molecules will experience dipole-dipole forces as their primary IMF. So remember, dipole means polar, so dipole-dipole would be between two polar molecules. So this results, again, when we have, with our polar molecules, we have a partial positive and a partial negative end to our molecules, our polar molecules. Those are going to create an attraction with another polar molecule. So dipole-dipole attractions can be represented in terms of looking at polarizability, kind of ignore that little part there. So over here, the higher electronegativity atoms, remember, are going to be that partial negative. The lower electronegativity atoms are going to be the partial positive. It's also influenced by the geometry of the molecule and where everything is. So just keep that in mind. Molecules with greater dipole moments will attract each other more strongly, which we'll get into electronegativity and the geometry. Okay, attractions between polar molecules, so these dipole-dipole attractions, are typically stronger than the London dispersion forces between the nonpolar molecules. However, when you are given data like melting points and boiling points, you must use the data in order to figure out what it has stronger IMFs. So this is important. The LDFs in a nonpolar molecules can sometimes be stronger than the LDF and dipole-dipole attractions between polar molecules. So this is where we're going to get into practice where we might find that a nonpolar molecule has a higher melting point or boiling point than a polar molecule. So we're going to have to talk about how those LDFs are actually stronger than the polar molecules, LDFs, and dipole-dipoles together. Okay, so dipole-dipoles occur between polar molecules. The greater the dipole moment of that polar molecule, the stronger the dipole-dipole attraction. So one special type of dipole-dipole attraction is called hydrogen bonding. Hydrogen bonding is not a bond. It is just a really strong type of dipole-dipole force, still an IMF, even though it has bonding in the name. So it occurs when a hydrogen atom is covalently bonded to a highly electronegative atom. And this is only going to include nitrogen, oxygen, and fluorine only. And the hydrogen has to be directly bonded to one of those three. That hydrogen will become attracted to the negative end of a dipole formed by a different highly electronegative atom, whether it's nitrogen, oxygen, or fluorine. So this can occur between separate molecules. So you would have your hydrogen bonded to oxygen, and then it creates this hydrogen bond attraction to the oxygen in another molecule. So you're looking for hydrogen, if you look down here, where I have my drawing, hydrogen's covalently bonded to fluorine, oxygen, or nitrogen. Okay, I'm looking at this guy right here. And then it's going to have an attraction to another fluorine, oxygen, or nitrogen. Okay, and that's represented by that dashed line there. So you need to be able to identify the bond versus the IMF and where those can occur. And it's very specific. Sometimes you will actually see a hydrogen bond formed between atoms within the same molecule. But again, you're looking for the same pattern. Here we have hydrogen that's directly bonded to oxygen, and then we have a separate oxygen atom, and then a hydrogen bond is going to form between them, and it's just happening within the same molecule. Okay, this is typically a very strong dipole-dipole attraction, which causes a much higher melting point and boiling point than we would expect when we look at trends and that type of thing. So you'll see that in a variety of questions. So some other types of intermolecular forces of attraction that you should be aware of as we go through identifying and describing is going to be here ion dipole force. So this is between an ion and a polar molecule. So especially when we get into solubility and mixing things together, that these are going to become more important, but I still want you to be aware of them. And think about Coulombic attraction for all of these. The strength of the force is going to increase as the magnitude of the charge increases, and also as the ionic radius of the ion changes. So as the ionic radius becomes smaller, so you have a shorter distance, and if the charge increases, you're going to create a stronger strength, also in terms of the dipole of the polar molecule. So again, all going back to Coulombic attraction. Ion-induced dipole force, this is between an ion and a nonpolar molecule. So anytime you see induced dipole, you're talking about nonpolar. That ion induces or causes a temporary shift of electrons in a nonpolar molecule, which then creates this attraction between them. So again, based on Coulombic attraction, you can figure out which is going to have a stronger ion-induced dipole force based on the ion's radius, charge, as well as the polarizability of the nonpolar molecule. And then dipole-induced dipole is going to be between polar and nonpolar. Dipole between an induced dipole. The polar molecule induces a dipole in a nonpolar molecule, and that creates an attraction between them. Again, these three are really going to come into play when we deal with solubility, but you are going to have to be able to identify them right now. Really, we're going to be talking about in terms of London dispersion forces, dipole-dipole, and hydrogen bonding. All right, I know that was a lot. We're going to take a lot of time this week kind of going through this and answering questions about it, but you definitely need to take your time to go through this on your own and do the practice questions.